explain only little variance. That could mean that in 2D plot, we might not well explain the clusters, the variance of clusters. Maybe if we use 3D plot, the result will be more clear. So the summary of this homework, we get a similar, also almost similar result between different methods. So P1 is in one cluster, and P16 and 19 is another, and the rest of the station is another cluster. That's my presentation. Thanks, Stephen.
You mentioned you have not standardized your data sets. So I'm just wondering what is going on if you do the analysis after standardization.
I get using, if I do the optimal numbers of clusters, I get all 15 or 16, like because the majority of this method can get is 15. So I'm not sure if that's wrong. Yeah, because I don't know if that's really 15 or it's just method cannot calculate more.
I think it also depends on the distance matrix you use, because the Euclidean distance for Manhattan distance that somehow that would highlight the importance of the very dominant species. Just as I say, you take the difference and take the square, and the distance would be mainly driven by the dominant taxon. So in this case, that if you didn't use the standardized data set, maybe you should change to the other distance metrics like a Brett Curtis that somehow measure the relative importance or measures the contribution in a relative sense.
Okay.
I think that would be for you to get more reliable results instead of just if you show a very outstanding outliers and the outgroups.
Yeah. Okay, thank you.
Yeah, but it's really good. Thank you.
Thank you.
You're okay with like turning those in half? Yeah. I think that's going to be better.
Okay.
Just this one.
Okay. So in last week that we give you a brief introduction about the classification, and the classification that we use the hierarchical method or non-hierarchical method like K-means to do the classification. But yeah, so the classification, it ends to just divide your data set into different groups according to the multivariate property. Big noise. Yeah. So last week that we
uh, um, we just give brief introduction for the cluster analysis and the non-hierarchical method like k-means. And here today, I would like to show you the other method called discriminant analysis that used to identify whether two or more groups are different. So just as you can see, the purpose of this method is to know the extent to which it is possible to separate two or more group of individual given the measurements of individual on multiple variables. So it is still under a multivariate framework. And so for each individual, or we say the sampling objects, they consist of many more than one variables. And we use these variables to identify whether we can separate this into two or more groups. But when we do this kind of separation, we have to validate whether this kind of separation, is accurate, or is there anything happen that data cannot easily separate those high-dimensional objects. So the purpose is to assign the new individuals that have the same set of variable measurements. For example, when we just measure the 5 variables, in the features iris data, they have 4 variables about the sepal and the flower shape, right? And if we have new individuals, coming to our library, can we correctly identify or make the correct assignment for the new individuals to the existing group? So that is the purpose. So when we want to add one or more sampling objects into our data set, can we correctly identify their group? So this is a very interesting case that's about the birds. If we can do some measurements on the shape of their bone and the heads, kind of we call this a morphometric data set. In this morphometric data set, we just want to know if we know that these measurements, can we easily predict which birds can survive after winter and which will die after winter. So there's only 2 groups that we're gonna assign all these birds into the survival group or non-survival group based on these 5 measurements. Can we do that? So that is the purpose. If we can kind of construct a classification rule based on these variables, then next time when we just collect a new per individual data, and then we can assign whether, or we can make a prediction whether this our new collected data sets would be assigned to the survival group or non-survival group. So this is also kind of a prediction if we collect a new data set, and we construct the classification rule based on all these 49 sampling objects. We also say this is our library. So it is our library set or training set. So you will hear those terms in modern machine learning. And then we could have our out of sample or the test set to test whether the model, the mathematical model that we constructed is useful or not. Okay. So what is the simple idea about the discrimination? So last week we introduced there are lots of distance measures. So the most intuitive way is to measure the distance metrics, the distance between those sampling objects. And then for each individual can be allocated or can be assigned to the group which that is the most close to. So we can just try to calculate the distance, and also we can just compare the distance between each individual or between the individual and the centroid, and then that will be the easiest way to assign the sampling object. And then here we could use like just in the last week we introduced that the Mahano-Bis distance. Yeah, and Mahano-Bis distance, just as I mentioned, is standardized with respect to their standard covariance structure. So actually, the points A and B actually have the same Mahano-Bis distance from the center mu. So you can use this approach, but it is not a very systematic way to use just use the distance and say, well, just try to compare which is the shortest distance between those data set and the centroid. And if we don't know what is the centroid in some cases that would not be a really good way to assign the individual A and B to a group. Yeah, especially when there's the other group that have some distribution in the multi-dimensional space really close to the existing one. So there would be the other approach called discriminant analysis. So what is discriminant analysis? The end of discriminant analysis is to find a function, and this function, a function of our collected multivariate data, and we use that function to separate the group as much as possible. So what is the function looks like? So in discriminate, the canonical discriminant analysis, we find a simplest linear function which can be calculated by the linear combination of these multiple variables. And this function, after this computation, we hope to maximize the ratio of sum of square between groups to that of the within groups. The sum of square between groups and the sum of square within groups. So that is the function we're going to find. So if we want to make a function, and so in canonical discriminant analysis, it could be a linear combination of our variables. So that is the kind of an inner product between our variables with a linear combination coefficients. Right, it is kind of an inner product between these. So it will be a very simple function. So how can we find this function? How can we find this linear combination coefficient? So that is the purpose of our analysis. So the aim is to find this kind of linear combination coefficients that makes the transform the data with the largest between group variation, but minimize the within group variation. What does this mean? Let's check this graphical presentation. If we have our data set like this, including blue, yellow, and red data points, and this is only a two-dimensional case, so it should be pretty easy. And then, if our purpose is to find a linear combination of our function, actually that means what? If we can find a unit access vector here, we actually we call this vector A. What is what is the meaning of the inner product? It means basically just the projection. We just project our data points on this unit access vector. So actually that is also a vector of our linear combination coefficient. So these two are equivalents. The projection on this vector means the linear combination between our data sets, with the linear combination coefficients. And then if we can just do the projection, so we project our data sets on these lines, and there are three groups. So our as we know that so far we don't know what is the identity of this vector. So it could be like this way, or it could be like this way. So depending on how you select these unit vectors, and you do the projection, and then after the projection, the end is to maximize the between groups variation, just like this purple one. So consider we have three groups, right? So we also have the three type of between group variation. So that is the between group variation. Actually, we consider the variation between the group centroid. Just like this one, and this one. We hope this this kind of distance or the sum of square difference would be maximized. But on the other hand, we would like to minimize our within groups variation. So within the blue groups, we hope after the projection, this variation could be minimized for whatever blue, yellow, or red groups. So that is our purpose, to find unit vectors. And after we select the unit vector, we project our data on this unit vector, and then we can just try to minimize the within group variation, but maximize the between group variation. So that is the purpose of this algorithm. And then I will just try to briefly introduce the algorithm. So in the following the computation detail, you don't have to fully understand all these details, but I still would like to let you know the idea and how the ideas to solve this issue. So considering we are going to find a linear coefficient A1, A2 to AP, considering we have a multiple P variables. And then our purpose is to maximize this ratio, the sum of squares between group over the sum of square within group. And we call this F ratio, because this is quite similar with our ANOVA analysis, right? Just like the sum of square or mean square errors, between and within groups. So in this kind of framework, then we're gonna just maximize these measures. this ratio. If we can maximize these ratios, then the unit vectors we select to maximize this ratio is the one we're gonna to, or we hope to find. So let me just briefly go through the algorithm. That X is the data matrix. So we're gonna find a unit vectors 8, and this is the linear product or the linear combination of between our data and the unit vector, the linear combination coefficients, such that this ratio will be maximized. But how can we maximize this? This would be a mathematical question. It's a mathematical problem that we're going to solve. To maximize this, we probably need to somehow simplify this question, because it looks quite a little bit complicated. So the way that we're gonna use to maximize this ratio can be started from the decomposition of sum of square of y. I'm not sure if you still remember that the total sum of square of this transformed data could be decomposed to the two parts, the within group variation and the between group variation. And basically, this is not special, not unique for this the grouping question. In the regression analysis, you can still do the decomposition of sum of square. Sorry, where?
And the white box. Behind the screen.
Okay. I'm not sure if so what is total sum of square? It is kind of just like you take the difference.
Is there another one?
Okay, maybe yes. Yeah, this method. So you take the difference between the data and the average, and you take a square and you sum them up. So that is the definition of the total sum of square, right? Okay, and this could be further decomposed into different components. So how could I do this? For example, we can do this computation. Okay, so we subtract this term and add them back. So actually, this is totally equivalent to the previous presentation, right? And then based on the expansion, we can easily find this. Oh, sorry. The xn is the kind of a model prediction, or the average value predicted by your model. So in this case, in the classification progress, the xn's might be just like your group average. Right. So but that is in classification question. as in regression, the xm's would be just like the you're equal to the intercept plus sorry, it's not x. Okay, maybe just like this one. So in regression, the model prediction or the model average would be like this one, a linear function. So whatever it looks like, it just we can say that is call it the xm or the model average model prediction. Okay, so that means that we can just compare this one. We can just do the expansion. Yeah, based on this computation. So it's equal to this. So I think you all know that the a plus b tan squared equal to a squared plus 2 multiplied by a and b and plus the b squared. So just like this, you can expand this presentation easily, like that. And then this is okay, just like this. And what's that? This is actually in this case, it is kind of the within group. In a classification rule, this is would be a bit within group sum of square, right? Because each data point just minus it just subtracts the group means from your data points. So they and take the square and sum them up. So that is within group sum of square. And this term actually is so-called the between group, right? Between group sum of square. And I will claim this cross product equal to 0. So how can I say this? So it won't be a very difficult proof, but I will just explain this in a graphical presentation. So consider this is our data set X, and if we do the model fitting like this using a least square approach, or we do the linear combinational projection, that is, we can get our fitting values. That is the model average. So the difference between our data points and the model average is actually we call the residual. Right? So this is actually the residual. Residual cross the model average and the total average. Because this is a projection, so the residual would be orthogonal, would be uncorrelated with our model prediction or model average. So this should equal to 0. Because they are the residual is orthogonal to your model prediction. And how about this? In fact, the total average is just a special or the degenerate case of the model prediction. considering the linear regression like this, if we let the b equal to 0, then we only have the intercept. And the intercept is just equal to the total average of your data set. So in this case, in fact, there is one of the solution equal to the total average, and the total average is also is also a degenerate form of your model prediction. So that is also orthogonal to your residual. So this part will also be 0. So that we can eliminate the cross term equal to 0. So that would be the variation decomposition. So we can decompose the total sum of square of variation into within group sum of square and the between group sum of square. And there's no cross term. Okay. So that is the way that we do this. So considering this is kind of a centralized matrix H. So this actually equal to the data, because this is multiplied by an identity matrix, so it is just the data itself, but they just we can just subtract this part. This part actually helps us to calculate the average values. And so this is kind of this matrix H is just kind of a centered matrix that helps us to calculate the total sum of square like this. And just as I say, the total sum of square can be further decomposed to the within group sum of square and between group sum of square. And then after some matrix computation, then we can use this kind of centered matrix to do the computation, and eventually we can write down the form, the matrix form of between sum of square and within sum of square. And here you can see this is actually the within sum of square of our data set, but we need to project either the x our data set to the unit vector, and so you can see there is a quadratic terms for the between groups within group sum of square and quadratic terms for the within group sum of square. Okay, so that is the final one that we want to use it to get our maximization for this. Okay. So sorry, that would be a mistake. That would be the maxima. Sorry, not minima. I'm sorry. Okay. This one. So what is our maxima means? That means that we want to find the optimizer of A that such that the following function could be maximized. So after the computation of our matrix, in matrix computation, that equal to this ratio could be presented like this, the ratio of this matrix quadratic form. And since the A, the unit vector, is a free vector to be selected whatever that, so we can just make a constraint that the denominator equal to 1. So this optimization problem could be further simplified. So if we just make this denominator equal to 1, and then we can simply maximize the numerator. We under some constraint of this, the within group the sum of square arrows equal to 1. So this becomes a constraint optimization problem. So I'm not very sure if you learn how to do the optimization under some constraints. There is a way called the Lagrange multiplier. I'm not sure if you learned this from your calculus. If no, then I would briefly go through this method. The Lagrange multiplier is to do the optimization of the function f of x under the constraints of some functions equal to 0. Like this. Oh, so you cannot only make one constraint, but you can also make two or more constraints to the optimization of this function. And this kind of a constraint optimization problem is equivalent to you gonna optimize this form, the f of x minus a constant called lambda multiplied by the G1, the constraint function. So we call this constant Lagrange multiplier. And this could be proved by the implicit function theorem, but I won't let you know this detail. But in any case, in this case, that the constraint function is that it's the within group sum of square arrow equal to 1. And then this the target function we're gonna make this we want to maximize this. So based on the Lagrange multiplier method, that we actually want to maximize this and minus the Lagrange multiplier multiplied by the constraint function. So this is also a maximized function, not a minimized function. Okay. So how could we make the optimization with respect to the function like this? So in calculus, we just take the first derivative and then the first derivative equal to 0, right? So just like you can do the same things. So you take the first derivative with respect to the unit vector A, and then the equation equal to 0. So you can solve this equation just like this. It actually just like the between group sum of square matrix multiplied by our target optimizer A and equal to the Lagrange multiplier multiplied by the within group the sum of square and multiplied by this A. And what is this? So we can just do some rearrangements, and we can say this these two the products of between group and the within group inverse matrix multiplied by these vectors would equal to a constant multiplied by this vector. So that means what is this? That means that A is an eigenvector of this matrix, the B multiplied by W inverse. So that means this, if we want to find a proper optimizer of A, then we must do the eigen decomposition to find the eigenvector of this matrix. And the Lagrange multiplier and the constants is just the eigenvalue of this matrix. So the algorithm becomes very simple. It's just to do or just to solve the eigenvalue problem of this matrix. That's it. So if we just do the eigenvalue analysis for the between group variation, between group sum of square and within group sum of square, and then we can find different eigenvectors. So this is actually those are eigenvectors of this matrix, and actually we can find more than one eigenvectors if the dimension of our data set is P, then we can find 1, 2, 3, 4, 5 until P eigenvectors. So for each eigenvectors, we can we can do the linear combinations with our data points, and then that is the projection. Yeah, so we project our data points on the eigenvectors. And because this matrix is still a symmetry, so that those eigenvectors are actually orthogonal. Means after the projection, that you project on the first axis and you project on the second axis, the value on the first axis would be orthogonal or uncorrelated with the second. So that means these two are kind of independent. So then makes us enable to use more than one canonical functions to do the classification. So we will say this is we have found our canonical discriminant function based on the eigen decomposition of this matrix. Okay, so you can see the Y1 capture the group difference as much as possible, and Y2 capture the rest of the variation as much as possible. But those variation will not displayed by the first canonical function. So, and the following are pretty much the same statements. Yeah, they just do the orthogonal projections on different directions. But the purpose is to maximize the between group sum of square and minimize within group sum of square. Right. And we can also test the significance for our discriminant analysis or discriminant functions. So actually, there are several tests can be used in discriminant analysis. Here, I just want you to show you one of the methods that we can use. We call it Wilks lambda statistics. This Wilks lambda statistics is kind of a multivariate version of F-test. But if you still remember that in F-test, what is the test statistics? That is in ANOVA, right? So what time is it? What time is it? We have to 10. Okay, so it's time to take break.
It's okay.
Okay. Oh, so yeah, it's okay. Let's take 10 minutes breaks. Okay, so that just starts the second part of our lecture today. So now we have the many of one or more discriminant functions, and then we want to test whether these discriminant functions are significant or not. So what is the significance? That we just try to say those discriminant functions are useful, are not null, behave like null functions. So here we just use the so-called Wilk lambda statistics. Just as I said, the Wilk lambda statistics is a multi-dimensional version of the F-test. But instead of the F-test that we used in ANOVA analysis, in ANOVA analysis we should in ANOVA we use the F ratio, like the mean square arrow, and the mean square arrow of our regression. But here you can see this is the F ratio here is in the opposite way. It is equal to the within group sum of square, but this is actually just like the sum square of the arrows. And then here is the total sum divided by the total sum of square. But since this is a matrix, and this is actually the values in unit variance methods, so how can we do? We cannot let the F values equal to the ratio of the matrix. So one way is to take the determinant. So why we take the determinant? The determinant in a matrix or high dimensional analysis is just like a volume of this matrix can expand. So if the volume is larger, then we say this variation is because it is larger. So that's why we take the determinant. And then the matrix becomes a value, a scalar. So here the essay, so on the null hypothesis, we will say that between sum of square arrows should be equal to 0, because that means your classification doesn't work. It makes everything the same. You cannot distinguish anything. So that is the null hypothesis. So remember that this the total sum of square equal to the sum of square between plus sum of square within. Right. So if this is close to 0, then we'll say the F ratio will close to 1 on the null hypothesis. So here we get this another name. Say it's lambda, capital lambda. So that is the basic idea of this test statistics. So you just take the ratio of the determinants of your covariance function, and then you can, just like your ANOVA table, you can have the statistics, and you can have two degrees of freedom with respect to the total sum of square and the within sum of square. And then you could calculate these Wilks lambdas, test the statistics, and then you could do the parametric statistical test based on these tested statistics. But this test can be done only if we admit our data follows multivariate normal distribution. If it is not obviously non-multivariate normal distribution, how can we do? We can still calculate these test statistics, but just don't let it be used to test the Wilks lambda's probability distribution. We can generate the distribution from Bootstrap, or we can use the other way to do or we can use the randomization test to generate a normal distribution of this lambda statistics and compare the normal distribution generated by the randomization, and we compare our realized or observed tested statistics with respect to the normal distribution. And that is the way you can do that. Still have a very meaningful tested statistics, but just we don't assume any underlying probability distribution like a multivariate normal to your data set. So you can still calculate this ratio, still quite meaningful, right? Okay. The second test will be this one. It's just we can test whether the eigenvalue is large enough. So just as I say, we do the eigenvalue decomposition for the kind of the between group, within group ratio matrix, and then we get the eigenvalue. If the eigenvalue is large enough, that means that our projection is effectively captures those variations. And if it is not, then this value will really close to 0, right? Because it's 1 plus lambda, and the lambda approach to 0, and this part will also approach to 0. And this is the standardization with respect to the number. Actually, this is with respect to the parameter numbers, or so-called degree of freedom. And this tested statistics under the multivariate normal assumptions would be approximate to the chi-square distribution. So basically, this is from the likelihood ratio test. Have you ever heard about this? The likelihood ratio test? The likelihood. The likelihood ratio test. So the likelihood ratio test is also a ratio that is your likelihood. Sorry. The likelihood calculated under normal hypothesis, and the likelihood calculated under null hypothesis unions alternative hypothesis. This one. So this is so-called the likelihood ratio statistics, and in general, we hope this ratio will be as small as possible, and there is a large sample property suggests that the -2 multiplied by natural log likelihood ratio would approximate the chi-square distribution. So that is this test is based on the local likelihood ratio test that follow the chi-square distribution. And then you can try to use the test statistics to check whether the ice eigenvalue or the ice discriminant analysis is significant or not. Yeah, of course you can also do it by the randomization test. That would be totally fine. And to compute the normal distribution instead of using the chi-square distribution, because that is kind of a large sample property. Okay, so there's some assumptions that we should notice uh, during in the discriminant analysis. First is that within group covariance matrix, the W is the set for all groups. Otherwise, we can have many within group covariance matrix that really complicated the algorithm I just showed you. Okay, and for the significant test, the data need to follow the multivariate normal distribution, especially for the first test, this one. We should follow the multivariate normal distribution. Otherwise, we cannot get a proper approximation of the X or the Wilks-Landa's probability distribution. But for this one, it won't assume the multivariate normal distribution, but it needs to assume you have a larger sample. You have a larger sample size, so the likelihood ratio test is somehow very okay. It needs the larger sample size to do so. So yeah. So in either case, you could use the computation based on the randomization or bootstrap. For the other requirement is that the determinant, is non-zero. The determinant is non-zero means this part that the total sum squared determinant should be non-zero. Otherwise, this value will go infinity. So how can we will have this? The determinant means the determinant equals is zero value. It usually happens when Lone sphericals are highly collinear. And then and here we have to note that even our data set cannot meet all these assumptions. That it doesn't mean that the discriminant analysis is rubbish, but you can still apply the discriminant analysis and try to find whether this discriminant function can help you to make a distinguish among different groups. If you can still reach really high accuracy, then just use it. Don't worry about it too much. So this is the example based on the Fisher's Irish data, 3 kind of Irish species, and 4 measurements about flower morphology. And then this is kind of the 4 variables and their relationship among these variables. And then when applying the discriminant analysis, and then we can firstly calculate the group means, and then we can calculate the within group and between group the sum of squared matrix, and then we can do the eigenanalysis for this sum of square matrix and get the linear combination coefficients, and that is actually the unit vector we seek to project your data on those axes, and then we could calculate the eigenvalue that actually just the proportion of the variation explained by your discriminant functions. And so this is discriminant analysis. So once we did the projection on this axis, you can clearly find the 3 groups. Actually, those groups can separate quite well. But you can see the group 2 and group 3 have a closer relationship. Means maybe we may make some mistakes. Yeah, for the individual belongs to group 2 or group 3. Okay. this is once again this is the visualization of this discriminant analysis. Just find a univector axis and do the projection on this axis, and you will get this kind of data set. And that is, I think this is the just the y-axis is the frequency, so it's a histogram, it's the frequency distribution along this the axis of the discriminant analysis. Okay. So now if we can have a new data set coming to our lab, where maybe you can just collect a new data set from somewhere, and you need to decide you want to decide which group should this new data set belongs to. So there's the two ways you can do that. The first way is that you just calculate the Euclidean distance between the new data points with respect to all the others individual sampling objects, and then you could find you could sum it up and find which groups which group have the minimize the sum of the multivariate distance. And if you find a group with the minimal sum of multivariate distance, then you try to assign this new data point to the group. Or you can, this probably a bit time consuming. So in the other case, you can just compare with their centroid. So you can just compare with their centroid, and then you determine which centroid or which group have the centroid that lies really close to our new data point. So in this case, you can also determine how to assign those groups. But in fact, you also need to project the new collected data points onto the uni axis vector. So that means you have to calculate the discriminant variable, the discriminant function. You need to use a discriminant function to calculate do the calculation and find. For example, now we can have a new data points coming to our lab, and then we have already know the linear combination coefficients. That is the discriminant function, and then we just put the new collected data on the discriminated function. If we found this the transformed data lies here, then we will say it is really close to the group 1, and then we will assign the new data point to the group 1, or you can check where you could find the new data point, the transform the new data point, and determines whether you want to assign those new data points to the existing groups. So that is also this is not this assignment, so can not only use for the new data points, but you can also use those old data points. You can also use the old data points, to make the computation with respect to the distance. The distance between each data points in the library set, with all the other data points, and you can determine whether this assignment is correct or not. So this is the case here. So not only you can do such kind of the classification rules for the new data points, you can also apply the classification rule for the existing data points in the library, and you could have the source groups. There in iris data there are 15 data points for each species, and then you apply the discriminant function again for each data points, even if they are already in the library data sets, but you can still assign those data points again, and you will find sometimes in most of cases there has no any mistakes. Both the assignment are corrected. If they are from the first species, they will be assigned to the first species groups, and the second and third. So the diagonal the value in the diagonal elements are actually indicates the correctness of your discriminant analysis, and the others maybe just you also can also make a mistakes even those data points are already in your library. And this kind of a mistake or the error rate is a good indicator for also a good indicator for you to say whether this classification or your predetermined group is good or not. If, for example, we have a predetermined groups like our seasonal group, spring, summer, autumn, but whether this predetermined group can really have the distinguishable characteristics in the multivariate data set. If it is not, you will make the mistake on those off-diagonal region. You can check. Yeah, so instead of just using the statistical significant test, that you can also check this by the correctness of the statements. Yeah, for the library data set and also for the new data set, for new data. Okay. Yeah, that's it. So, and you will probably have the other question is that sometimes we don't know how many variables is enough to do a correct discrimination. So there's also called a stepwise discriminant function analysis. So that could help you to determine how many and what kind of variables is useful to then you do the discrimination for the for your data sets. So here in iris data, they could just have a 4 variables, but in most of cases you could have tens, even hundreds of variables, and you have no idea which variables are more useful to then you discriminate your target species or your target groups. So in this case, you need to kind of just try and error to see what kind to add removing variables from a discriminated function one by one, and it's a try and error algorithm, and to see whether the discrimination can be significantly improved. Yeah, so you could have many ways, just like the stabilized regression, forward or backward regression, and you could have set up several useful criteria like the F statistics, whether the F statistics improve or not, and or you can also use the lambda value to say that the proportion of the explained variable as a criteria, and if this criteria can be improved, then we add these new variables. Otherwise, we exclude the existing variables. So just like stabilize or the forward and backwards variable selection to determine the optimal variable set to carry out the discriminant analysis. Okay, and select. Okay, so yeah, as I say, just try to avoid selecting those variables as strongly correlated. Otherwise, it will have a problem of collinearity and redundant information that will be too redundant. Yeah, and also makes your your discriminant analysis more variable. So it's not good. Okay, and that is so the other say the judgment true classification of individual. Well, actually the judgment is just you leave one out. You leave one your data point out of the computation of discriminant functions, and then you use, for example, if you have n data points, and for each time you leave one out, so that means you only use the rest of n minus one data points to calculate the discriminant function or discriminant analysis, and to make a predict the assignment of this data point you have to leave one out. So this is quite a useful way to check. We also call it leave one out cross validation. And but here, because it's quite old method, they also say this is a judgment. So basically they are the same. Just leave one out, use the n minus one data point to predict the rest of the one data points, and for each time you change the one you throw away from the library set, so you conduct this analysis n times. So you conduct this discriminant analysis n times, then you can also check whether the discrimination is good or not. To avoid the inferential observation, a few points could be very influential in determining the centroid of the groups, the group. So in this case, if you jot out this inferential observation or even outliers, that would make your results more stable. So this nice algorithm extrudes some individual and estimates the discriminating function or remain data classification of the individual I, repeat for all i's, and then try to estimate the percent of correct classification. And usually there will be let your correctness decrease a little bit, but that would let you have a better ability to predict the data out of your library set. So that means that could give you better generalization for your algorithm. Okay, so yeah, so that is the kind of a tested set to possibly to assign the ungrouped individuals, into the groups based on the Mahalo distance, in the sense of Mahalo distance after the discriminate function transformation, and also you can also get the error rates, from those training data set, and also get the error rates from the tested data set. So you have two different error rates based on your library set, the leave one out cross validation, or the new data sets that are not used to train the discriminant functions. So they're so-called the out-of-sample prediction. Okay, so you could try to practice the discriminant analysis based on the iris data, and then I would start to introduce a more general or more I would say the other methods that are more suitable for the categorical data or the categorical classifier. This is so-called decision tree learning. So this is a learning algorithm. So it's actually really popular in machine learning, AI, or something like that. So the idea is still quite similar with the discriminant analysis. Just try to maximize or minimize some properties that you wish to, and when you just set up the classification tool, but they just made some adjustments to make this the classification could be more generalized to different type of data. So now, so far we use the continuous data to calculate the linear combination and projection. But so what if we could have some data set like the categorical data, for example, whether the weather is good or not, yes or no, or do we have clear water, yes or no? Just you could have a really we can have a very only a few states of your variables. In this case, that you can use the decision tree learning that will give you better ideas. For example, if you want to know whether your dad will go play badminton tomorrow, yeah, I'll say it's Saturday. How will you decide whether or not to, your dad decides whether to play or not? Let's say your dad go out by checking the following variables like the weather, whether the air temperature, whether it is hot or cold. So it's a kind of a binary data variables. And then you can also have some continuous data like the speed of winds, or you can check this from the Central Weather Bureaus, and you can also get the humidity data, and also how the weather is sunny, cloudy, or rainy. You have three states, only have three states for your data sets, but these states might or might not be in the ordinal sense, means the cloudy is maybe also in the ordinal sense in terms of the humidity. Okay. Anyway, but just like a categorical data, it is not a continuous data like the sepal or the length of your flower sepal or petal. So this is kind of a categorical data, and you can still use this categorical data to make a decision or make a classification for your data sets. So taking all these factors into account to decide whether your dad want to go out for playing badminton or not. So that is what the data set looks like. So for example, you just do a survey for the last 10 times, the last 10 Saturdays, and you will make the records for this weather index, and then so the weather, temperature, humidity, winds. So they are basically they are all the categorical variables, and then the final target is whether your dad played the badminton or not. Yes, no, yes, no. So basically we just want to use this the X to make a prediction for the Y. So it is in fact it is also a linear model or a regression program we have. So it is a binary response variables. So your response variable Y is a binary variable, only have a yes or no, 0 or 1. But you can also get a more complicated the response variable, the state of response variable. It will be also fun. Okay, so the collected you can do that. So you collect the data for all these variables, all these 4 variables for the last 10 records, and then check the state of these variables, and use this table to predict whether your data right or not. Then we can use a learning algorithm called the decision tree. So the decision tree is taking all the possible paths that take into account and lead to the final decision following a tree-like structure. So this is a tree-like structure. So you may start from any variables you like, you can start from weather, but actually we will introduce the algorithm behind how you selected those variables and how to determine each division of your data points. So in these trees you can have a different node, and for each node that would give you a condition. For example, the weather, whether it could be sunny, cloudy, or rainy. So it is not necessary to be a dichotomous treat. So it could be they have three divisions at one time, three or more divisions at one time. Okay, so you can see this is the simplistic case. So in cloudy case, that always go to the to play badminton. But if it is in a sunny days, that will also check the humidity, or they just feel the humidity. If this is still a normal days, maybe yes. But if the humidity is so high that it would be not so comfortable, then we'll refuse to play the badminton. But and this is a rainy day, and rainy day in most cases it is not. But if the wind speed is weak, then yes. So this is kind of decision tree. Okay, and this is the other example. Yeah, for us to predict whether the IUCN conservation status of fish populations, different fish populations. Then we can also we can collect those the data about the maximum age or the reproduction rates, and whether it is all fish, yes or no, or the other there are only three variables we collected, and we can just classify the fish population into different levels or groups: vulnerable, less concerned, in danger. So there are three groups that we're gonna assign the fish populations. So yeah, you can see from the beginning it will be a really simple question about whether the fish population is overfishing or not. So it's a yes or no question. So that means it's just a binary categorical variables. But you can have some more complicated continuous variables. So in these variables, you need to set up a question about the threshold value, whether the maximum age of 10 or younger, or the reproduction rates should be larger than such threshold value. And I will also tell you how to select those threshold value in order to implement the classification. Okay, that is it. Okay, so there's a more complicated tree mixed up with both the binary variable and the continuous variables. So that is cutoff value, and the cutoff value won't be the same if they put into different nodes. And then, I forget to say that. So this is a tree. So for each trees we have a root. So that is the starting point of the trees. And then we can have a knot, in the tree, between the tree branch. So in terminal knot, we will say it is a leaf. It is a leaf. So there's no more branch. So it means they are terminal. They are at the terminal nodes. And actually, as a terminal nodes, you have to make your decision. You have to make your assignment for your data sets. Okay, so it's a terminal node or loops, and this is also called node, but they are called internal nodes. Okay, and these are the terminal nodes or leaf, and if we we reach the leaf, it means there's no more branch, and we need to make decisions to assign whether those groups should be yeah, which need to assign those data set into different groups. So makes we make the decision. So the classification tree are designed for the response or dependent variables with finite number of unordered values, like plain Bennington, yes or not, or about the IUCN conservation level, endangered, less concerned, or vulnerable. Yeah, so these are actually a finite number of unordered values. So this is so-called unordered categorical variables. And the prediction error can be measured in terms of misclassification cost. So the misclassification cost that would be very similar as what we just learned from discriminant analysis. You could have you can calculate the error rate or how many mistakes you made, yeah, during your classification. And this is some also have a loss functions, yeah, when you have already constructed your decision tree or at each step of your decision, the division of your data set. So there will be a more general method called the classification and regression tree, and abbreviated as CART analysis. The CART analysis including both the classification tree and the regression tree. Here, the regression tree, I would say the dependent variable y is more continuous, or at least as an ordinal variables. Yeah. So this actually they are all regression for me, but people would just like to try to distinguish those two into two differently. But for me, they are all the regression analysis. Okay, so let's try to build up the classification tree. So what time is it?
I don't know.
11. 11 already?
Yeah.
Okay, so yeah, this takes 10 minutes break. this continuous the classification trees. Yeah. For example, if we want to predict whether a species can live in such a habitat, then this is probably the fish species. So in a river, so we collected the data like that, the urban land use, good water quality, and low connectivity. And then this is what our data set looks like. That is the X, the independent variables, and the red one is the dependent variable or response variables, and they are all categorical. And then we can try to implement the algorithms by measuring the impurity or so-called the entropy. So then we can just measure and compare the impurity or the entropies, to determine which separation is the best. So from the roots, then we now have three type of different variables that, for example, the land use. Depending on the land use, we can have two states. Yes, there is a land use, or no, there is no land use. And then for each separation, okay, you can have your fish, your species presence, yes or no, yes or no. And then you can calculate the sum of the impurity or entropy index, like the Gini index that is invented by economists. Yeah, this is 1 minus the summation of the frequency square. So it's really similar with the Chanel diversity index that you have ever seen. But you can also use Chanel, of course. And that actually considering the impurity or entropy of this division. So the goal is to minimize the entropy for each divisions. So here you can see if we start from the urban land use, and we started from the good water quality use, then we can have different divisions, and for each divisions we can calculate the Gini index, and there is also weighted by the proportion of the sample size. So this the weighted average. Because you can calculate the Gini index from yes or from no. So there is two, and you take the average with respect to the sample size. Okay. So here we can see if we started from the good water quality, that would give you lower the Gini index, and then you can use this one to decide. Oh, okay, then that started from the water quality as our roots. Okay, and then we can keep divide your data sets into different, based on different classification, or depending on the state or your independent variables. Okay. So there are still the other impurity measures like classification, error rates. So here you can, or the Gini index, or you can use the information entropy. Actually, this is even more common than the Gini index for decision tree analysis. And then we get so when is the decision tree? When is the impurity measures get maximized? It is when every frequency are equal, have an equal frequency. For example, if we make such a division and we get the how 50% of the data showing the presence of the fish, and the other 50% also showing there's the absence of this species. So if we make this, this is the maximal entropy, or the maximum of the impurity. So So that is actually what we get in the idea we can get from the Shanghai Diversity Index, because when every species have the same proportion or the frequency, that means they are all really even. So in this kind of situation, the even or the uniformly even conditions implies the maximum entropy, the maximum. Because many of us are ecologists, so would like to maximize the entropy that is the diversity, right? But in this decision tree, we want to minimize the entropy that makes each discrimination quite useful, but not just makes everything equal. That you cannot, it is not effective division of your data set. So okay, and if you have interest, you can use the Lagrange multiplier to prove to find the optimization of this entropy, and you will find this is a constant, implying everything should be equal to the set. Okay, anyway, that we can just keep growing the tree. So now we found that the good quality or the good water quality or low connectivity, and then you can have calculate the Gini index. Oh, okay. Now they calculate the others is low connectivity, yes or not, and this one seems like larger than the good water quality, right? So it means that we use this as our note, and then it divided the data set into two parts, and then we can just keep growing the tree by keep assigning the classification rule to divide the data set into finer groups. See, okay. Okay. Weird, but okay. In any case. Okay, so you can just try to apply the different. You can try to apply the different categorical independent variable and the make the division until you find the further divisions won't improve the impurity. This one, you calculate this. If you just keep make a division, and you won't find an improvement, and you will get your leaf. That is the terminal rule. Okay. So the steps that us quickly review the step in the classification tree. Just calculate the Gini index, impurity index, or the information entropy, and find if the division have the lowest score, lowest impurity or entropy, and then there's no point to when there's no point to separating the node anymore, it becomes a leaf. Just keep continuing to do the separation and division. Okay. Okay, and if the division can give you more improvements in the Gini index, then just keep doing so. So that will be pretty easy. So, but how to deal with the numerical or continuous data? So, like this is the temperature. So the temperature can also influence whether the fish is present or not. So the algorithm is like that. So you can order all the fish habitats by the temperature, and you calculate the average the values between two adjacent objectives, and then you calculate the impurity values for the separation determined by each average values. So that is you take those average values as a different threshold, and you test and you calculate the Gini index or the impurity index on the different threshold, larger or equal or smaller than these values. So they kind of also a kind of dichotomous divisions, but just based on those threshold values and calculates, and then you will, when you get the minimum impurity measures, and that means this threshold value is a proper threshold value to make you to do the kind of the classification. So now it's 20.5 degrees Celsius. Yes, is the best threshold for you to use to divide your data set. Okay, so that is the visualize for the classification tree. So we can still apply those independent variable as the continuous variables, but you can just find those threshold cutting points based on the ordered averaged values between the nearby data points, and so you could have 1 and 2 and 3 different cutoff values, and then you can. So once you determine the threshold, you can also then the tree keeps growing. Okay, so you can also deal with the data with multiple categories. Like there are lots of rivers. At least you can find 3 names here. So this, if there are multiple categories, or the categorical variables have multiple states, then you can use one. You can use one of the states, for example, the river into the Barron rivers, yes or no, and Cooper River, yes or no. Or you can use the kind of a union, or the union of these the states. For example, is the river the Cooper River or Barron River? If yes or no. Yes. So it should that you to give you more complicated combination for those nodes, under those 3 nodes, and you can keep divide your data set based on these more complicated classification. Okay, so okay, in addition to use to minimize the impurities, in machine learning sometimes they will say use this term more often. This is called the information gap, and actually that is the entropy difference between before and after the divisions. So when you do the divisions, or you then the tree growing, then you will decrease the entropy, or decrease the impurity. So this is kind of defined as a very general information gap, and you can just calculate the information gap for different variables. If the variable have different states, more than 2 states, that would be also fine, and you try to minimize that for each of the division. So let's see the example tree analysis in Irish data. This one. So okay, so you could just try to run the classification tree analysis, and they will give you several outputs, and that it will be detailed, and you can check by yourself. Then, but basically, those index are quite easy to make computation. Basically, just say how many entities could be correctly identified. So. Okay, so that is the classification tree based on our example. So there are many library or package available for conducting the classification tree analysis. You can pick out whatever you like to do your classification tree analysis, and they also give you this kind of the results and tell you well, you can reassign your or make the assignment for each data point, or you can divide your data set properly based on this classification rule. So for each node, it noted as a unique classification rule. Okay, and that's also the example. So just try to find whatever you like. And the final algorithm is a regression tree. The regression tree is very similar with the classification tree, except for they consider the continuous variables, so the sustainability is a continuous proportion. And in the classification tree, we use the unordered or categorical response variable yes or no, 0 or 1 to as our targets. So regression trees for for continuous variables, and prediction error typically can be measured based on the sum of square difference between the observed and predicted values. So just like the regression analysis, we calculate, we aim to minimize the least square error. And here, this is quite similar to we can calculate the sum of square the difference between the observed and the predicted values. So this is a really simple example. We can a typical regression, then we just find a regression line to fit the data, and it will be looks pretty good to have such kind of a linear fitting. But in some cases, if our data set looks a bit weird, like this, then it is really difficult to find a linear fittings come across these data points. So in this case, we can reconstruct the regression tree for the highly nonlinear response variables respect to those independent variables. Okay, so here we can use the temperature. Even though there's only one independent variable, we can construct a different classification rule at each nodes and determine the relationship between the temperature and the sustainability. So here, the first one, classification would be whether the temperature is smaller than 14.5 degrees. And if yes, okay, the sustainability index, equal, the average sustainability equal to 4.2%. And if no, then we keep divide the data points. Okay, like this. Okay. So in this case, the regression tree is trying to divide your data set or the response into different parts, and for each part that we fit the data, by just using average values. So eventually, we can apply those. We can also combine with all the other categories, for example, to make a prediction. Okay, so you can just mix up with the temperature, with the age, with the gender, male or female. That's also a mix up between the continuous and the categorical explanatory variables. Okay, so but how can we determine a root based on the continuous variables? So you can just try to split your data. In either case, you can just make a split. For example, you can make a split, make a divisions. As the temperature around 20 something. Okay, and then you calculate the mean. For the threshold value. For the data set smaller than the threshold value and data set larger than the threshold value, and calculate the mean, the mean, and then you can also calculate the sum of square error, sum of square residual, and you can so you can just try and error to find the optimal threshold values for this for the temperature data, and then here you can see the best threshold could be set up here about the 14.5 degrees Celsius like this, and so if you set this, you calculate the mean over there, and you calculate the mean over there, and this kind of division give you the smallest residual sum of square. Okay, and we can divide the regression data set into different parts, and for each part, so this is the first part, and then you can determine the second part. Give you you calculate the average value larger than the threshold or smaller than the threshold, and then divide the data set. So you kind of just like a piecewise fittings for the relationship between water temperature and the suitability. Okay, so yeah, so you can just do the you can now determine different roots. Also, you have to determine the roots of these trees. So you compare the minimal the tree with the minimal sum of square residual for those candidate variables, and pick up the candidates is based on this criteria. So now because the response variable y is continuous, so it is pretty easy to calculate this the sum of square residual. Yeah, in categorical data, you can just calculate the frequency or the proportion in a sense of frequency or proportion. But in this case, you can calculate the difference, the square of the difference. That is the sum of square of this residual. Okay, so that's this. When do we start dividing the node? The regression tree algorithm have a really high risk in overfitting the data. Think about that. You can just keep divide your data set and calculate the average, and the average value just equal to your observed data points, and that makes your sum of square errors equal to 0. So that is we could have a really high risk in overfitting the data. So there are several rules that we can probably apply. So for example, we can make the division only when there are more than some minimum number of observation. Typically, the minimum number is about 20 points. So if this division less than 20 data points, then we just stop here. So we just stop here as the terminal node. It will just becomes a leaf. So we did not further divide the data set if the sub data set is less than 20. Okay, so there's a few remarks for the regression tree algorithms. So this is also still a type of a decision tree, but for each leaf, they instead of present as yes or no or some categorical variable that's normal, in regression trees will give you a report of the numerical value. It usually predicted the average, and then you divide the observation by trying different threshold, and then calculating your sum of square residual at each step. And then you also need to determine the roots from different categorical variable candidates. And and a node becomes a leaf when there are fewer observations than some minimal numbers. But in fact, there are the other criteria to terminate these algorithms. I will tell you later. So, but you need to remember that by minimizing the sum of squares residual, you've got a really high risk to have an overfitting problem because you can just divide it to a single data point for each leaf, and that is useless classification, and it cannot be generalized if a new data point that will come to your data sets, then that would fail the prediction. Okay, so the other way to solve the overfitting property is just try to add the penalty and the tree complexity. So the penalty is basically the number of leaves. We need to make some penalty about the leaves. We don't want to that each data set become the independent leaves. So we can add this tree complexity penalty here, but there is a penalty coefficient. Then the penalty coefficient usually can be determined by the cross validation methods. So you just leave 1 hour and then calculate the performance and then determine which penalty factor is the most suitable for this data set. So okay, this is the residual. Okay, residual sample square, and okay, so when there's no any division, you can see this. You will get the maximal sample square residual, but when you just keep doing the tree reconstruction, then the tree growing, then you will further decrease the residual sum of square, but it is not true because they will just monotonically decrease until each data point becomes a leaf. So you will prevent this happens that you add the penalty on the number of leaves. Okay, so okay, just like that. So you can by adding the penalty factor, and that is a penalty factor equal to 10,000, and you can calculate the tree score, and that is kind of equal to the residual sample square plus the penalty, and then you will try to minimize this under this kind of tree that with intermediate complexity, but still usefully decrease the residual sum of square. So in this case, we will select this tree. But you will see when we set the penalty factor differently, we will get totally different trees. So which tree would be better? It would depends on which tree can give you the highest accuracy in correctly assign the new data points. Or you can do the cross validation, just leave 1 hour and use the others to construct the tree and to make the prediction for the assignment. Okay, so different tree will give you a sequence of trees, but we have to select it based on some criteria. So, and there's also called the pruning algorithm. So just try to make the tree simplified. So you can just divide the full data set into training data and testing data. So the training data is just like a library data you use to build up a flow trees, and there is a series of subtree that can minimize the tree scope with under certain penalty factor, and then you can use this tree to test your testing data and to see whether it is good to make a correct prediction. And that is so-called the out-of-sample prediction. But you can also do the cross validation by leave some data set out, and then you just use this kind of method to you leave one part of a subset of the data out of the tree construction and use the rest of one to construct a tree and make a prediction. And then you change to the other part of tree. So this is actually, we call this here I say the X4 cross validation. What's that? It's basically, it's quite simple and easy. So now we have for example, we have n data points. Then for if we use the leaving one out the cross validation, so each time we select a data points out of our data sets, and then we can have we can use the rest of the others to that's our as the training data, or not training data. So the rest of our data set to reconstruct a tree and then make a prediction. We can do this, as you remember, we can do this for n times because we have n data points. But this case would be very time consuming if n is very large. For example, if you got 10,000 data points, then that means you need to do the computation for 10,000 times. Then that would be really time consuming. So the other way to do the cross validation would be much easier. That would be say, okay, so this is the data points. Okay, all your data points. Then for tenfold, maybe we can just cut this data set into 10 pieces. Can cut this data set into 10 pieces, and for each time we move one of the pieces out of our training data and use the rest of, for example, if I cut this into 10 pieces, then I use the rest of the 9 pieces data set to make prediction on this, and for in this computation. Here I just need to calculate, for example, 10 times of the tree of the decision trees reconstruction. So that would be save lots of times when doing so. So you try to you can try to use difference for maybe 3, 4. Then we will say this 10-4 cross validation. So next time when you see these terms, just remember that just try to do the cross validation in an easier way, not try to do this for each data points. Okay. So and then we can use the tenfold or anyway the one out the cross validation to determine the alpha value that the penalty give us the optimal result, and then. Once we determine this, we can just go back and reconstruct the tree based on the whole data set. That will give you a finalized regression tree. Okay, so try to do this kind of algorithm. Okay, and in this kind of regression tree algorithm, there will also have an issue about the pre-pruning or post-pruning. That pre-pruning means that we could just check the each node from the beginning, from the each root to avoid the overfitting. So we can more effectively stop the additional division. For the post-pruning, maybe we can just reconstruct a decision tree or regression tree. Then we check all the non-leaf nodes to see whether from the bottom to the roots. So for example, if we can have the tree like that, then we can just from the bottom, so we can check all these nodes to see whether those nodes are necessary or not. If this is not necessary, then we drop it. Okay. So that is so-called a post-pruning. So there are lots of algorithms that you then you simplify, then you give you a more useful tree that can use to make a correct assignments, not only for your training data but also for the tested data. If we can we can make a correct prediction for all the tested data, that is we can have a really good auto sample forecast ability, or that we have a bad ability of generalization. Generalization means we can have a very good auto sample forecast. Sorry. Anyway, you will see these terms in machine learning. Generalization. If an algorithm have a good ability of the generalization, means they have a really good ability to make the auto sample forecast. That is the sample that are not involved in your training data to construct a tree or do the others. So that this is quite common terms using machine learning. So, okay, there is the green decision tree based on that is kind of you can use the different maybe J. Okay, I'm not sure, but anyway, you can find the library or package easily. So the advantage of using decision tree, because the tree is very intuitive and easy to explain to people, even though people are not an expert, they will be really acceptable for those tree presentations. Yeah, and sometimes the linear regression is a little bit difficult, especially there are more than one explanatory variables, and there will be in a high dimensional explanation, and people will just feel so sick about this. But yeah, so this give you a graphical presentation, and tree can also can help you to handle the qualitative predictor, like the categorical variables without creating the dummy variables. But the advantage of trees is also obvious. It's really easy to get the overfitting result, and it won't give you a function of this the statistical fitting function. So it's just like a tree, but it's maybe quite obvious or quite intuitive, but you cannot use this to do the further more advanced analysis. Okay, this is like a tree. Yeah, do not have the same level of accuracy as the other regression classification approach, and tree are also not very robust. Sometimes if you add the other part of data set, it will give you a larger change in the final tree. So the tree topology isn't a very reliable or robust result. So that means we need to apply the cross validation to try to make the reconstruction trees more in a more reliable way. But sometimes you will hear some more advanced approach called the random forest. Forest means lots of trees, right? So you can by creating lots of trees and then determine the tree topology from tens of thousands of trees, and then that will finally give you a more reliable tree. So you probably learn this, but I won't go this into detail because this kind of also a machine learning techniques. Okay, so by aggregating many decision trees, just like this, I say using methods like bagging, random forest, boosting, blah blah blah. There's so many algorithm that can help to integrate lots of tree into one and most reliable tree. That is the all of these the materials today. And here I just let you to do your homework by also still use the domain copypath data set to perform the discriminant analysis, canonical discriminant analysis, and create the discriminate plots. So that means you make the projection and you have the classification table. The classification table means that you can just assign all the data point in the library data and then to see whether your assignment based on the discriminant function is correct or not. So this you can have, for example, but how many groups in the copypath community?
I don't.
Is there any predetermined groups?
I don't think there's predetermined groups, but they have like seasonal data.
Okay.
Like you have like 3 seasons among several cruises, so it could be these.
Okay, so if we can identify those seasons, the seasons from the data points, then maybe we use the season as a predetermined groups, and then try to make a classification table with respect to the seasons. Okay. And then you based on this classification, you need to test whether season such a predetermined group is useful or not. Whether this kind of the grouping or classification is really useful to explain how different among those copypath community, copypath composition. Okay. And okay, you use the same data set to perform the classification analysis to tell about the story about. Do we have the environmental data?
Yeah, they have.
Oh, okay, maybe. Okay, so try to do your analysis based on this copypath data and try to conduct the discriminant analysis and the classification tree analysis. Okay, so you are allowed to use whatever building function in MATLAB or R. Okay, and that's it. Oh, so who is the next one? Give a presentation.
Do we have any volunteers for next week's presentation? No. Has everyone presented at least once? Or no? I don't remember. So we're all going to present at some point, so you better do it soon than later during this semester. Do we have volunteers? No. Who didn't present yet? Raise your hand. So if there are only 3 people, so among 3 of you, decide who is going to be the next 2. No volunteers. Alright, it's going to be 2 of you. Alright. This homework next
就是讲是，就是如果我的那个data 是，就是会影响，就是会被比较大的数据影响的话，用哪个方法比较好？
可能我觉得用那个 Bracketis 就是那种我们常常有时候有比较强调那个relative 的那个 abundance， 就是 proportion 的那个，就是因为它有些数值可能太大，所以你可能把它当做 proportion 的。像它那个是我记得那个 Bracketis 是 standardized with respect to 那个 maximum Manhattan distance 之类的。那你就是不是
看那个绝对量的那个变化，那个时候就会比较不容易被一些 dominant species 影响，因为通常在 community ecology 里面，我们比较想要知道说就是 composition 的这个问题，那统计一般就是